For the line integral over the positively oriented c of x squared y squared dx plus xy dy, we're going to evaluate directly and use Green's theorem. C is the arc of the parabola y equals x squared from 0, 0 to 1, 1, and the line segments from 1, 1 to 0, 1, and from 0, 1 to 0, 0. Let's see what that looks like. So we've got the arc of the parabola from 0, 0 to 1, 1, and then the point 1, 1 to 0, 1, and then the point 0, 1 back to 0, 0. So our curve C actually consists of three curves. We're going to call them C1, we're going to call them C1, C2, and C3. Now, to evaluate this directly, we need to parameterize all three of those curves. So go ahead and pause here and get parameterizations for C1, C2, and C3. For the parabola, we let x equal t so that y equals t squared. T goes from 0 to 1, so dx is dt and dy is 2t dt. For the segment going from 1, 1 to 0, 1, we're using the formula that we have for the vector function that connects one point to another. The result is that x is 1 minus t, y is 1, and so dx is negative dt, dy is 0. By the way, y equals 1 along that horizontal segment should make sense because along the whole horizontal segment, y equals 1. Therefore, for C3, having x be 0 makes sense, and y is 1 minus t. Again, for C2 and C3, t goes from 0 to 1. For C3, dx becomes 0, dy becomes negative dt. Now we're going to put this together for the original integral, which was the line integral over C of x squared y squared dx plus xy dy. And pause here so you can complete that for the sum of C1, C2, and C3. Substituting our expressions for C for x squared y squared dx plus xy dy for C1 is going to give us t to the 6th plus 2t to the 4th dt, because we have x squared y squared times dx plus xy times dy. For C2, we have negative dt times 1 minus t, the quantity squared, times 1 squared. And then for dy, we have 0, and so there's not a second term like there is in the first integral. Even better for the third integral, x is 0, since there's a factor of x in both terms of the original integral, that gives us a result of 0. And at this point, it's the power rule all around. T to the 6th evaluates to 1/7 t to the 7th, 2t to the 4th evaluates to 2/5 times t to the 5th, but t is going from 0 to 1. For the second integral, I wrote the integrand incorrectly. It's 1 minus t, the quantity squared. So we have a u, which is 1 minus t. A du is negative dt, and so we can use the power rule on that expression, which I somehow did correctly there. 1 minus t, the quantity cubed over 3. That last bit's evaluated from 0 to 1. Ultimately, here we end up with a result of 22 over 105. Now, to use Green's theorem, I'm first going to remind us what it says. The line integral over c of p dx, say it with me, is equal plus q dy, maybe don't say it with me, is equal to the double integral over d of the partial of q with respect to x minus the partial of p with respect to y dA. I recommend writing it down pretty much anytime you need to use it for a while anyway, because then it'll drill it into your heads. The original integral was the line integral over c of x squared y squared dx plus xy dy. Of course, there's no reason to memorize that. And then we'll remind ourselves of what the region D is, x and y axes there, and we have a parabola that goes from 0, 0 to 1, 1. There's our region D. What I'd like for you to do is set up and compute the integral using Green's theorem at this point. All right, comparing our parts, p dx is equal to x squared y squared dx, and therefore p of xy must equal x squared y squared. So the partial of p with respect to y is equal to 2x squared y. Q dy is equal to x squared dy, so q of xy is equal to xy. So the partial of q with respect to y, with respect to x, is equal to y. We're going to use those results to flesh out the double integral. So we end up with the double integral from 0 to 1 of the integral from x squared to 1 of y minus 2x squared y. That's partial of q with respect to x minus partial of p with respect to y. I chose the order of integration dy dx. In choosing dy first, I am considering basically a vertical segment there within our region D, and it starts at the parabola, so x squared is the lower limit, and it ends at the horizontal line, so 1 is the upper limit. Integrating with respect to y using the power rule is going to give me 1/2 y squared minus x squared y squared. That's going to be evaluated from x squared to 1. The whole thing is still in the integral from 0 to 1 dx. Substituting 1 in place of y gives me 1/2 minus x squared. Substituting x squared in place of y gives me 1/2 x to the 4th minus x to the 6th. Using the power rule, we get 1/2 x minus 1/3 x cubed minus 1/10 x to the 5th plus 1/7 x to the 7th evaluated from 0 to 1 for a result of, big surprise, same as before, 22 over 105. So comparing these two techniques this time, we had to identify p and q so that we could find their partials and then compute the integral. We had to make sure we represented the integral, or the region D, in terms of our limits of integration. That was a little bit of work, but it stands in contrast to the first way we did it, which required us to parameterize 3 different curves and write down 3 different integrals, one of which turned out to be 0, but that won't always be the case. And the point here is really you now have a couple of different ways to approach an exercise like this.